Okay, honestly, whenever I see these are one of my favorite questions. Lots of words in it. Honestly, like not even kidding, it feels like it's the most standard. That's why. Like previous questions, they took easy things and they made it difficult by adding like that a question, or like they took that table and then they just like messed it all up. So it's like really hard to interpret because of the inverse. Not much you can do with these types of problems. Super straightforward. So let's get started in it. Okay, it says this: the volume of a spherical hot air balloon expands inside the air, yada yada yada. So basically, we have a balloon that's increasing. Um, so then from here, it says estimate the radius of the balloon when t is equal to 5.4 using tangent line approximation. So basically, we're going to use our tangent line. We're going to need to make a tangent line. Um, and is your estimate greater or less than? So basically, what we're going to do is we need to find what r of 5 is. So what we're going to do is we're going to have r of 5 y minus equals r prime of 5 times by x minus 5, basically, in this case. So we're using our equation here. The other thing that you could do is you could just use the slope and go from there. So you can either plug in all of your points into here. I'll show you how to do that, but I'm also going to show you how to just kind of mentally play with the idea of slope. So then here's what we have. We have tangent line approximation, estimate the radius using the tangent line when t is equal to 5. So the radius is 50 feet. So then what we know is r of 5 equals 30. And then what we're going to do is estimate concave down twice differential. The radius of the sphere is given by the volume. So I was looking at this and I was like, I swear I'm taking crazy pills, because there's no way that they would be able to do this without giving me what r prime is. And they did have a table. I just must have missed it when I was copying, because basically the formatting of the practice AP exam, which I'm going to be uploading, it's harder to write on. So in order to make it cleaner, I cut it, and apparently I cut it out. So good job, Mr. Mori, doing great. So here's what we have right now. This is your table. So like I said, I need r prime of 5 as well. So we're going to say r prime of 5, and r prime of 5 in this case is going to be equal to 2. So option number 1, you can plug it in here. So we have y minus 30 equals 2 times by x minus 5. And then we're trying to figure out what is y going to be when x is 5. Well, t, I guess, in this case. So we're going to say y minus 30 equals 2 times, or excuse me, it's going to be 5.4. 5.4 minus 5. So we have y minus 30 equals 2 times 0.4. So y equals 30.8. So this is one way that you can do it using your point slope form. That's totally very valid. For me, though, because it's just an approximation and they don't check on work too often, what I normally do instead is I look at this, and then I just kind of play with the slope over here. And if I know I want to say what is r of 5.4 approximately, I know that my run changed 0.4. So if I were to say my slope is 2, that means if my run changed 0.4, my rise had to change 0.8. So this is going to be 30.8 approximately. Again, if you want to write it out, you can. It'll save you a little bit of heartache if you get the answer wrong. But for me, saving time is pretty valuable. That's why I look at it this way. All right, next for B, it says find the rate of change of the volume of the balloon with respect to time when t is equal to 5. So indicate units of measure. Find the rate of change of the volume. So basically what we're going to do is we have volume, and it gave us our volume here. It said volume equals 4 over 3 pi r cubed. Now when I'm taking the derivative of this, I'm taking it with respect to time. So dv dt equals 4 over 3 pi times 3r squared dr dt. Now if you remember, this was our related rates types of problems here, when we have a different variable than the one we're deriving with respect to. So because of that, we have to add this additional dr dt. So we're saying, what is this going to be? And if you wanted to write this outside of our function, you could have written r prime of t as well, and then v prime of t. So if you wanted to keep it in function notation, you could do it this way as well. But again, it's totally up to you how you want to do it. I'm going to leave it like this because it's a little more familiar to you guys. And then so what we're going to do is, my goal for B, it says find the rate of change of the balloon with respect to time t is equal to 5, indicates units of measure, so we'll worry about that after. So my radius is going to be equal to 5, so dv dt evaluated at t is equal to 5, or excuse me, yeah, t is equal to 5, is equal to 4 pi r. In this case, my r of 5 was given as 300, or 30, excuse me. Squared times by dr dt evaluated at t is equal to 5. So it's saying, what is the slope of my r? What is the rate of change of my r with respect to time when t is equal to 5? And according to this over here, it's 2. So times by 2. So then from here, dv dt evaluated at t is equal to 5 is going to be equal to, what is that, 900 for 8 pi times 900, and then from here that's 7200 pi. Now what's happening here is I'm taking the change of volume with respect to time, and the change of volume is feet cubed per minute. So make sure you have your units. You can chuck them at the end if you would like. Generally, they want you to do it from the top down. However, I believe if you have magical units, it's not the end of the world, but you should be doing it as you're going. Again, this is just a simple related rates question. They give you your volume function, you take the derivative, and when you take the derivative, don't forget your derivative is with respect to time, so you do need to add on that additional dr dt. You can't derive for free. Okay, let's look at C. C says use a right Riemann sum with 5 subintervals indicated by data, yada yada yada, to approximate use correct meanings. Okay, so again, the reason I'm skimming through isn't because it's not important to read, but for me, I'm reading, I'm processing it. I don't think you need me to read it out loud to you. If I'm reading it too quickly, you can pause it, or you can, have yours on the side, because I will have this uploaded, and then you can be reading it on your own time. But it's just to keep the videos a little shorter, because this is honestly my second run through on this. First run through, the videos were like 25-30 minutes each, because I was just kind of blabbering on as I was kind of reading, underlining all the little things. But I figured I'll run through it, I'll tell you what I'm looking at, tell you at the big pictures. However, instead of going over all the constant possibilities, I figure as we do these more often, you'll see more of the constant possibilities. But again, feel free to ask questions. So doing this here, we're doing our right Riemann sum. So I'm going here, this way, so on and so forth. Now, if you remember with Riemann sums, I have this over here, and we're going like this. We're making rectangles, and we're just adding the areas of the rectangles together. So all you're going to do when you're going to add the rectangles is you need 2 things. You need a base and you need a height. Now, as a reminder, your base is the change in time. Your height is the right number here. And the reason it's the right number is because we're doing a right approximation. If I said left-handed, you would take the left number of the rectangle, because again, it's like this. I'm taking this height wherever it is, I'm extending it to my next point, and I'm just drawing a rectangle here. But this height is constant, and it was whatever I was on the right side. That's why it's called a right Riemann sum, or right-handed Riemann sum. So let's get going. So the first area that I'm going to deal with is my height is going to be 0.5, and my change, my base, is going to be 1. And I'm going to add it to this next one here. My height is 0.6, and my change is going to be 4. Next over here, my height is going to be 1.2, and my change is going to be 2. Again, this is my change, On the right side, that's my height. This is my change. This is my height. Next, my change is then going to be 3, and my height was 2. And then finally, my change is 2, and my height is 4. So let's do this out. 0.5 plus 2.4 plus 2.4 plus 6 plus 8. So what is that? 4.8, 5.3 plus 14. So 19.3. Okay, it says 19.3. Let's read on just to make sure we didn't mess anything up. Okay, now it says using correct units, explain in terms of the radius of the balloon. So basically what this is telling me here is this is giving me the rate, the radius is increasing. Now if I integrate it, what I'm saying is all of those rates combined is giving me the total change of radius. So again, if I'm looking at the radius change, then when I integrate, I'm getting the total change of radius. So what this is going to do is this is going to be feet. And then what this means is the balloon changed its radius by a total of 19.3 feet. Okay. And then next, C, done. D, it says, is your approximation greater than or less than the actual? So it's saying we're comparing the two. Is it greater than or less than the actual? Now, I read through this, and there's a key that tells you whether it's above or below. It's concave down, number one. And number two, if you look at this, my numbers are constantly decreasing. Now, here's why that's important. If I draw this shape over here, it's concave down. If I'm looking here and I'm doing right-handed approximations on the left side, my boxes are bigger than my actual shape, which means that I'm over approximating the area. But if I'm doing right-hand approximations from here, you can see I'm missing little areas here because all of this missing because it's concave down and to the right. So if you're ever not sure, just draw it out. But your answer to this is it is an under approximation. And then the reason why is because since it is concave down, and we don't want to say it actually, since R of t is concave down and R prime of t is decreasing, then right hand approximation is under. Okay, so again, it's an underestimate just because of the way we drew our shape like this over here. If I went to the right here, again, if I started here and I went to the right, you would see it's an over approximation. But because it is decreasing, that means we're on this part of the concave down. So please be careful of that. You have to say concave down and decreasing. Also, I said it and I erased it, changed it to R of t. They don't like you saying it. They want you to reference it, reference the function as much as possible because they're saying, are you talking about your R prime function, your R function? So whenever you're writing these answers, try not to use generic what is it, like object pronouns or whatever, but try to actually be specific. All right, 5 down, last one.